Thank you all for being here. So I'm Chris Ceroici. Thanks for the introduction. I am going to be talking about PulseMedica, what we're doing and how we're using machine learning AI to treat vitreoretinal disease. So a bit about me, I did my PhD here at the U of A in the ECE department in Professor Roger Zemp's lab, mainly focusing on 3D ultrasound. I graduated in 2019, so the last 4 or 5 years I've been at PulseMedica, leading the machine learning team. And originally we started with, there's just 4 of us here in the cubicles in NREF. And now we're up to a little over 40 people in our office downtown here. Yeah, so I'm happy to talk about how we're using machine learning. And I actually did these slides on a flight back to Edmonton last night, so I don't know about timing. We'll see how it goes. I might come up short, so feel free to ask questions if you want to know more detail. Happy to expand if I'm able to. Go. Okay, yeah, just brief summary. We'll talk about what is PulseMedica doing, and I'll give you a spoiler. We're dealing with floaters, so we'll talk about what are floaters, and then how are we using machine learning to treat this condition. Skip through here. Okay, so floaters, eye floaters, are basically chunks of collagen or strings of collagen that are suspended in the gel in your eye, or the vitreous. And so you might have seen these. I'll skip to this example here. I like to show this as a demonstration of floaters. So anyone in the room see shapes like this when you look at a bright white background? I do. I see like almost this exact kind of shape when I look at this screen. So this is an eye floater. It's not just in your brain, it's an actual structure in your eye. And that's what PulseMedica is focusing on. And so around over actually 50% of the population has eye floaters. And around 5 to 10% of this population has severe eye floaters. So if you imagine that little string, but now it's not just a string, it's a giant dark blob in the center field of view, and it stays there. And it impacts your ability to drive, to work, to function. Tons of people have this, and there's really no treatment right now. It's actually the most common complaint from ophthalmologists that they get from patients, and they don't really have a great answer for this. There's no good diagnostic screening tools, and there's no way to treat these effectively. The only treatment is something called a vitrectomy, where they basically go into the eye and kind of suck out the vitreous, the gel, and replace it with a synthetic compound. And you can imagine this is very invasive, has lots of potential risks and side effects. So PulseMedica's goal is to come up with a non-invasive way to treat eye floaters, as well as build a system for how do we diagnose and characterize floaters so that we can address the issue with coming up with some measurement terms and characterizations that we can assign different kinds of floaters. Okay, so what are floaters? So I mentioned the vitreous. So the vitreous is basically the gel in your eye. So you have the lens in the front, and then the vitreous, and then your retina in the back. And for a long time, people assume the vitreous is just this kind of structural, homogeneous, passive fluid or gel. There's actually some complexity in the vitreous. It's there's kind of a meshwork of collagen and also these tubules that deliver nutrients to the front of the eye. And sometimes that collagen can get tangled or stuck and cause it to diffract light onto the retina. And that's typically what is responsible for floaters. And a lot of different environmental impacts can cause floaters, like head impacts, or even just aging. Over time, as we age, our vitreous becomes more solidified. And as that happens, it can kind of detach from the retina, which is completely normal. It's not really dangerous, but that can cause the release of additional collagen to flow into the vitreous and create floaters. So if you don't have floaters now, you might get them later in life, unfortunately. And so here's another diagram. This is can't remember what modality that is, but this is kind of a cross-sectional view of an eye showing someone with severe floaters. So I mentioned, here's the lens of the eye. And here's the retina. So the retina is where your photoreceptors are with collecting light and sensing light. It's sent to the brain. And then the vitreous is everything in the middle. And this is where floaters live, basically. And so PulseMedica's goal is we want to find these floaters. We want to diagnose and screen them, build a language around how do you measure a floater and how do you tell if someone is symptomatic or not, and then also come up with a method to treat them with a laser non-invasively. So right now in our treatment path, I'll just talk about where we are as a company. So we have 40-something employees. To actually build a product like this and sell it, we need to go through a bunch of different stages. We need to test first in animals to show that we can use our device safely. We then need to test in humans to show that we can effectively treat a floater. And then we need to go through clinical trials through FDA or Health Canada. So right now we're at the animal testing phase. We have a prototype device that we're testing. And so the basic idea for treatment is that we have this laser that is focusing on our floater in the vitreous and ablating it. There are many different types of lasers. So a typical laser you're probably thinking of would usually approach this with something called photocoagulation, which essentially means using heat. So you focus on a point and use heat to destroy that tissue. That's actually a challenge in the eye because the retina is also very sensitive to heat. So that means if you're focusing too close to the retina, that heat can actually kill off the photoreceptor cells, permanently damaging vision. So we're using a different laser called a femtosecond laser. Essentially, it's a laser that has these really short pulses on a scale of femtoseconds. And the mechanism that it uses to destroy tissue is actually not related to heat. It's actually ionizing the molecules, stripping away electrons so that we can ablate tissue here as our floaters without dispersing too much heat in the retina. That means we can treat floaters that are much closer to the retina, and those tend to be the floaters that are most symptomatic. So how are we using AI for this? We are, this is kind of just a summary of our treatment pathway. So we use AI to first detect floaters, and I'll get into more on what that means on the left there. This is essentially looking at a shadow of floaters projected on the retina. We're using AI to track those shadows. We then want to visualize and image the floaters in 3D. As you can imagine, floaters are suspended in the vitreous. They're basically these, if you imagine like a 3D geometry sloshing around in the vitreous, and we want to fire a laser at that, not just once, but potentially dozens of times to treat it, but it's constantly moving. So it's a challenging problem. You can't rely on just a human to guide this in real time. And then we ablate it with our femtosecond laser. So how are we using ML for this? So I mentioned already, we're using ML to detect and track floaters. We also use machine learning for reconstructing our 3D floaters. And then finally, there's a lot of ML involved in how we characterize and quantify floaters. So this is what I'll focus on. So first I'll talk about our imaging modalities. So how are we imaging floaters? What information can we get? One is a 2D imaging modality called SLO, scanning laser ophthalmoscope, which is essentially taking a picture of the retina. So you can just imagine that image I showed before, that was an SLO, kind of just like a 2D photograph of the retina, but using a laser. And 3D imaging modality called OCT, which is optical coherence tomography. And that's this green cone here, which is, you can imagine it coming out of the page. So this is capturing a 3D column of information. You'll notice it's quite narrow, and that's a limitation of OCT that is inherent, which is the speed that you can scan your OCT to capture larger volumes is limited, which normally wouldn't matter if you're just imaging the retina, something static. But because floaters are constantly moving, we have to limit our capture window to smaller areas so that we don't get motion blur as it moves around. So that's a unique challenge with floaters. But of course, we need that 3D information to properly image, characterize, and treat floaters. Here's just a summary of these modalities. So you have our 2D, SLO, This is an image or a video, so we're typically capturing these at 30 frames per second, and then our 3D volumes of our OCT. And another modality that we can use is fundus, basically another type of 2D image, this time actually like a camera instead of a laser. And then we also care about patient symptoms, so the reported subjective symptoms of the patient, because there is a neurological component to this. Some people can have the same kinds of floaters in their eye, but only one of them reports symptoms because people neuroadapt to floaters differently over time. Kind of like when you have your blind spot, you don't notice your blind spot all the time. Your brain adapts to it. One major problem we have, especially at the beginning, is that there are no public data sets of floaters. No one's really captured this kind of data before. So a lot of effort has gone into how do we synthesize data that is realistic enough that we can apply this to actual imaging data. And so here's some examples of synthesizing 3D floaters or simulated 3D floaters. We've also done the same for these 2D SLOs. So in this case, we've taken, this is not a real floater, but you imagine an actual floater geometry that we've measured with our OCT, and then use ray casting simulations to simulate how that shadow is projected onto the retina. So we've done a ton of stuff like that to try to build up our own internal data set. Also, right now, for the last 8 months, I believe, we've been collecting data from symptomatic patients at a site in Panama. And we actually just opened another site here in Edmonton to collect data from people here in Edmonton. So I mentioned 3D, 2D imaging modalities. So how are we using these? So 2D, our SLO, we're essentially looking at the projected shadows of floaters in the retina. So here we have our floater, and the SLO beam is kind of focusing here on the retina, but it's passing through the vitreous. So as it does that, it's going to pick up and get scattered and then generate these shadows on the retina. And that's a really useful way to guide where we want to aim our OCT to capture these in 3D. But it also presents a big challenge. We need to be able to detect these. So if you look at this image, can you see where the floaters are? I can't. It's basically impossible from a single frame at least. If I play this, so you can start to see it a little bit better. It's definitely not easy. I think if you look near the top, you'll start to see. What is that? This thing? That's just a reflection from the imaging system. Yeah. Yeah, an artifact. So you can kind of see it floating near the top. It's blocked by that little talking Ceroici. I'll skip to the part where you can see it. I can. Thank you. There we go. Yeah, this is real time. So you can kind of see some features of the floater there. Still not easy to detect, but that's our goal, is to build a system which can in real time. So we also, our ML inference needs to be in real time, 30 frames per second. We need to capture these, detect them, but also we need to track them. So we need to label them with an ID so that we can track multiple floaters over time, keep track of which ones we've already imaged, eventually which ones we've already treated, and then build kind of a library. So our approach has been to basically first stabilize these images. We want to remove all the background movement of the retina because the floaters move independent of the background retina. We then use a machine learning model. So we take a buffer of images over time. So I mentioned it's really hard to tell from a single frame. So we collect a buffer of images, pass those through a deep learning model to generate essentially a heat map of floater detection. And then this heat map is then used, it's passed into another algorithm, which will take all the newly detected floaters and compare that to all the previously detected floaters, look at their velocities, look at their shapes, and also some logic around if we know a floater can't appear down here and then disappear and appear over here. So we can add some restrictions that way, and then try to kind of discretize them by assigning the same ID or assigning a new ID if it's a newly detected floater. And so here's another example. This is the OCT on the right, but so the actual detection heat map, this is after the heat map. This is the actual detection contour on the left showing the floater. And so once we have this detection contour, we can then tell our OCT to scan. So that's that green box here. You imagine a cone coming out of its page. You can scan that area and then generate this this 3D volume over here. So this is the retina here at the bottom. This is the actual retina we're seeing here. And this is just a shadow. And then this is the actual floater structure that's casting that shadow. It's a pretty typical shape for a floater. We have a kind of a nucleus and then some strands that spread out from there. Yeah, it's tricky. So we can't for actual floaters, where it's one major effort right now for us is building test structures, test vessels. So there's a company in Calgary that can print 3D structures out of collagen. So supposedly the same material. And so we're printing out basically known geometries. We can then image with the same techniques and then make sure we're reconstructing the actual shapes that we care about. Yeah, we have our artificial eye. It's still an ongoing study of how do you best model vitreous. Egg white is one suggestion, but we tried all kinds of stuff. It's not simple. Cadavers are, yeah, it's tricky to get cadavers in the office lab. We've looked into it. But that would be ideal. But also the eye degrades very quickly after someone dies. So yeah, there's a lot of constraints there. Like the lens, for instance, starts to get cloudy very quickly, so you can't really image within a certain period after. Yeah, so that was floater tracking. Another big issue with us, a challenge for us is reconstruction. So I showed you a bunch of floaters. This is kind of a different stringy kind of floater. But there's a fundamental limitation with our OCT, which I had mentioned before, which is our scan speed. If we want to treat floaters accurately, yeah, go ahead. Sorry, what you're reporting? Yeah. Yeah, so what's actually happening here is, have you ever been to the ophthalmologist before, an optometrist? Basically, you sit with your chin on the chin rest, and there's a thing in front that you look into, and you see usually they'll have a little target that you stare at. That's basically what this is like for the patient. So they're completely awake. They can be blinking. We try to keep their head still, but it's, yeah, very non-invasive. Yeah, you might even be able to see a blink in this one. So if it blinks, typically you'll see like one of these slices is black or is cut off or shifted. So in this case, it's either not visible. They probably did blink because it takes around 5 seconds to capture this volume. It's hard to not blink for 5, especially because most of the patients we image are over the age of 70. Yeah, so that usually it's not super obstructive. So I mentioned it takes around 5, sometimes 10 seconds, depending on the size of that volume, which is a huge bottleneck for us because if we want to image these in real time and treat these floaters in real time, we need to know, we can't just rely on where the floater was 10 seconds ago. We need to know where it is right now in 3D so we can accurately plan where we're going to fire that laser. And so to solve this, we've looked into using sparse scanning. So instead of scanning, so an A scan is basically, if you imagine your volume and you just slice out a vertical column of pixels, that's an A scan, just looking down one vertical column. And so if we were to fully sample this, we would scan all the A scans we need across this volume of interest. But another approach that we looked into is what if we don't have our scanner perform a raster scan, which means kind of going back and forth throughout our volume, which is what we do now. Instead, we can plan a different kind of sparse pattern where it just kind of zips around in a sparse, maybe randomized way. that still covers some of the areas of interest, but doesn't fully sample that volume. We can then take that sparse set of A scans and then pass that through a reconstruction model. So in this case, we're using a vision transformer, and then reconstruct our full volume. So here's an example of that. This is not an actual floater. This is a synthetic floater, because to make this work, you need that ground truth volume, which we unfortunately don't have with floaters yet until we have some test vessels. So here's our original simulated floater. It's kind of a few different strings in different directions. Here's our sparsely sampled A scans. So this is only, so of our volume, we're only sampling 10% of those A scans. So this is what our model is seeing. This is the input. And then this is what we're able to reconstruct from that. And so with sampling only 10%, that means that we can speed up our imaging by a factor of 10, right? So instead of a imaging rate of 1 volume every 10 seconds, we can get a volume per second. And so that's one big advantage here. Yeah.
So the next slide.
From which?
So this is that we don't input and correct shipment. So we don't need the predicted volume.
You mean this input?
Yes.
You might, but like if you look at this string here, here in your sparsely sample, you only have like one small chunk. So to build a treatment plan, you might need to build, so what that might look like is kind of a spiral of treatment points that follows the geometry of each floater. Same thing here, another pattern of points that looks like that. So you need to know the bounds of that floater, the actual morphology. Yeah, we use that term a lot. So to build on that, we don't just have the OCT though, we also have these SLO images. So it's still focused on the retina. We're not actually seeing the floaters, but we see their projected shadows. So we've extended that to also be multimodal. So now our transformer sees not just the sparse set of A scans, but our full SLO volume or SLO image, which has those projected floater shadows. And so we can use both that information now to reconstruct our full volume. So here's an example of that. I didn't have an example of the same sample volume. This is a different one. But so now, and also I'm not showing the SLO here, but it is also a simulated SLO on a retina. We actually take a real retina, but then simulate our floater geometry shadows onto that retina. And so we sparsely sample. This time it's just 5%. We're able to get a pretty good reconstruction of that floater geometry. And interestingly, we can actually completely sparsify or sample none of our OCT and just rely on the SLO. And you get kind of what you expect, kind of a Z projection of our shadow in our reconstructed OCT. And so this is really interesting for us because one of our products is actually going to be a screening device, a lower cost screening device for floaters. And one of the big things that increases the price is the OCT, or 3D imaging system. So if we could build a device that only uses SLO and we can still learn useful characteristics like the distance from the retina or the shape of the floater in 3D, that would be really valuable. This is not going to get us there by itself, but there's other sources of information that we're currently working on. For example, we don't just have one SLO, we have a video of SLOs. And so even though you might not be able to learn about the exact geometry or depth from a single shadow frame, what if you have a video of that shadow changing over time? Can you then learn more about the 3D geometry? And yeah, so what this is leading towards, and the same thing applies to A scans as well. So we have each A scan actually has its own timestamp. So that means instead of treating it as a raster scan, where okay, I finished my raster, here's a new volume. You can treat each A scan as its own sample in a long train of samples with their own timestamps. And instead of, we kind of refer to it as frameless imaging. Every new A scan, every new SLO frame you have, you can now build a new reconstruction using all that prior information. And what that's leading more towards is around this dissociating morphology and pose. So if you're imaging a floater and you know roughly what that floater looks like in 3D, you flesh that out. Every future imaging session or sample now just needs to update the position and rotation of that morphology. Yeah, exactly. They might move a little bit and you can build that into the model. For the most part, though, they're just translating and rotating. Okay, another big task for us, the ML team specifically, is how do we characterize these floaters? And the holy grail is how do we look at data like this and then correlate that with patient symptoms? Because it can be really difficult. And there's sometimes unintuitive cases where you have patients who say they have really terrible floaters, but it seems less opaque or less or smaller on our OCT, or the opposite. They have like completely opaque, massive floaters, but they claim that they don't see that much, or it's barely a nuisance. So how can we measure useful parameters from what we're imaging and then correlate that with patient symptoms is a big challenge for us. And one challenge or one area that we focus on is how do we decide? So looking at a floater like this, we've imaged this and thresholded it to visualize it, but how do we know where the floater starts and ends? Because this is all vitreous, so it still has structure in it. And we can make a nice visualization, but then how do we come up with some methodology? So another way we use machine learning is to take volumes like that and then segment out the floater geometry based on the density and the morphology of those floaters. And yeah, so some of our analysis, we've basically broken down, I think we've imaged about 200 eyes at this point of symptomatic floater patients. And we've mostly categorized these into 3 different groups: speckled groups, lumped structures, so kind of with a nucleus and strings, and these kind of string flowing like floaters. And yeah, and so our challenge now is how can we further divide up these structures. I give some numbers to these in terms of opacity, how much light gets blocked by the floater, and then correlate that with patient symptoms. Yeah, so that's a summary of how we're using machine learning to treat floaters. Most of our efforts are around what technology barriers do we need to overcome to effectively build a treatment device? How can we image fast enough? How can we build a treatment plan and know where to fire our laser? Yeah, and currently we're hiring. We have a full-time machine learning scientist position currently open. We also hire interns. And if you're more on the software engineering side, we're also hiring software engineers all the time. And that's it. Thank you.